the topic environmental risk. We have 3 presentations. As in the previous presentation, we will have the 3 presentations one after the other, and we will have a general discussion, and we will also have some discussion also with an external panelist, with Stefan Rutger from PTB, and also in representing Eurados here as a stakeholder. And so I invite the first speaker, is Olivier Armant from ASNR, and he will talk about an AOP perspective in modeling cumulative risk.
Do you hear me? Yeah, put it live.
Hi everybody, yes, it's working perfect. So thank you very much for giving me the opportunity to give this talk, which is modeling of cumulative risk, an adverse outcome pathway perspective. This work is part of the Radon task 4.9, which is named Assessment of Combined Toxicity and Cumulative Risk. So human and ecosystem can be exposed to variety of different stressors and pollutants, and those environmental exposure, they are characterized by complex mixtures of different pollutants and substances, usually found in the environment at low concentration, but with chronic persistence. So the World Health Organization and the International Agency for Research on Cancer say or indicate that up to 9% of the cancer cases are attributable to toxic environmental exposure. In addition, non-genetic factors, that is lifestyle, environment, but also socioeconomic status, contribute to more than 70% of the overall risk of developing chronic diseases, not only cancer, but chronic diseases in general. So there is a need actually to better understand and better model those different environmental exposure, and the exposome concept was proposed in 2005 in order to complement what we know from genetic towards a more environmental perspective of understanding the environmental exposure to multiple pollution. And here, in the context of radio protection, we have to acknowledge that ionizing radiation found in the environment, but also for the exposure of medical use of radiation, is usually, and most of the case, a small part of this exposure. But being small doesn't mean that we have to ignore the contribution of ionizing radiation to the overall burden of the totality of those exposure to different kinds of substances and stressors. So we have to acknowledge that usually in the environment, human and ecosystems, they are exposed to multiple stressors, and this is not to avoid here a bad term, it's rather the norm than the exception. This is actually a bit contradictory to what is actually happening in toxicology field, because most of the toxicological data are obtained from single compounds using model animals, and usually we ignore actually the cumulative stress of ionizing radiation with other type of stressors. This is due mainly to the fact that it's difficult actually to attribute toxicity to ionizing radiation when it's found together with other stressors. It's also important to stress that it's not possible in the laboratory to assess and test all possible combination of stressors, because there is an infinity of combination. So environmental exposure is important, and in the context of radon, what I would like to stress here is that humans are usually not exposed chronically to radiation, but the exception can be radon, natural biota, that means the animals and wildlife, they can be exposed chronically to radiation, for instance in Fukushima and Chernobyl, but today I will focus on human and lung cancer. So we just need to recognize that a realistic exposure scenario is usually not monostressors, and we need to better understand and predict the impact of radiation in combination with other type of stressors and pollutants. So here I will provide you a very brief and simple case, which is the combined effect of radon and cigarette smoke. So the advantage of this case example is many data are available, both from epidemiology and radiobiology. And for what you saw this morning, there is a known interaction between radon and cigarette, which is usually considered to be synergistic. And in the literature, we will find the term submultiplicative, but it's deviate from classical additions of the risk. Current gaps that can be addressed here are usually related to personal thresholds and risk derived from personalized medicine, considering actually residential radiation level with smoking status and other factors like age and other type of pollutants. And here, simply resolving the mechanism interaction would facilitate the identification of signature that would help actually to support personalized prevention strategies. So here I would like to provide you an example of how we could better model effects from the exposure towards the effect. Exposome itself can be modeled conceptually with what we call aggregate exposure pathway, which is actually modeling part here of the exposome, focusing on tobacco smoke and radon. So the AEP is actually used here to model how, at the level of the exposures, tobacco smoke and radon will interact before it enters into the lung and in the body. Once it's into the body and interact with the cell, then we can use another framework, which is called the adverse outcome pathway, which will model how the effects, biological effects, are causally related until the occurrence of a disease, which is called here in the AOP framework an adverse outcome, in this case the lung cancer. So we use here those two concepts, aggregate exposure pathway and adverse outcome pathway, in order to better predict and describe the effect of combined exposure of radon to tobacco until the occurrence of lung cancer. So we have made in Radonome, we have developed a novel strategy in order to computationally model such framework from the existing knowledge using machine learning and what is available from the current existing databases present on PubMed, but also in AOP Wiki, which is a repository, StoreDB, that you know and heard already, and of other type of database which are related to toxicology, like DCGNet, GeneCard, and the comparative toxicogenomic databases. So all this knowledge is sparse around there, and we tried actually to use machine learning to gather all the available information to fuel this framework that I just showed you, AEP and AOP. I don't enter too much in the detail, but here I would like simply to stress that we are indeed limited to what is available, especially for PubMed. If an article is not providing actually the data, we cannot model our framework here. We cannot incorporate this knowledge. We did not actually use all the data which are produced by Radonome because of publication delay and so on. We are really dealing with what is available and published already openly. So I don't enter too much in the detail here, but we have descriptors for all the events from the exposure to lung cancer that describe the causative relationship of tobacco and radon leading to lung cancer. And those descriptors were actually the first task was to assess what are those data that are there in internet. This is a clustering of the data that we could gather. And the first take-home message that you can find here is that most of the data are actually from epidemiological studies. The cluster number 4 is actually the data which are describing effects, causal relationship from animal studies, and you see that there is little knowledge on the causal effect of radon or tobacco. Most of the knowledge is actually from epidemiological studies, which usually omits mechanistical understanding of the effects of lung cancer. The other thing that we can stress is that there is very few data from animal studies which relates to this lack of mechanistical understanding. Is it a problem or not? This is not for me to judge, but simply if we focus here on the exposure. So this diagram here shows you what we could gather from the available information, and what you saw this morning is actually represented here as this circular graph. Tobacco smoke and radon can indeed interact together. We had a very nice talk this morning about this effect, and possible synergy can happen at the level before inhalation, and as we saw also this morning, there is actually synergy or antagonism depending on how actually you are a heavy smoker or a light smoker. What we could also detect here is that there is a lack of study at environmental concentration of radon, environmental relevant concentration of radon. Most of this knowledge is actually derived from high level presence or in animal studies. For the biology part and causative way, I do not enter into the detail neither, but the available literature was synthesized here for radon and tobacco smoke, and we could detect two hubs of interaction which might explain the synergistic interaction of radon and smoke, possibly ROS production at DNA damage, nothing surprising, but this is making sense, and also mutations. We saw also this morning from epidemiological studies that particular mutations in proton oncogenes or other genes are important risk factors which could actually explain the progression toward lung cancer. So together, what I show you actually is not new. It's simply a simple way of presenting complex data from epidemiology and radiobiology. This is something that is important in our case. The other thing that I show you is that we can develop a machine learning approach to help such development. And the limitation here are that we do not apply in our assessment the bright voltage criteria. So far, this is something that is not made by human, and we don't have a computational approach to actually develop the bright voltage criteria that is usually made. So it's not fully automated, if this is something that I can do. So the other limitation is that we rely on what is published. So if you don't publish your data and they are not open, you cannot, we cannot use them. And this work is actually under publication here. Finally, and I will finish in 1 minute, the applicability of the frameworks together. So here we have a framework which is a nice opportunity for collaborative work. So here the idea is to use molecular data and epidemiologic data together, avoiding actually to omit part of the knowledge. So this is a simple but not simplistic framework. For communication and risk strategies, this can be useful as well towards stakeholders and also the public, because it's a simple representation of complex knowledge. It provides also an harmonized foundation for comparing or integrating the risk for radiation and chemical. And finally, in the context of combined exposure, this framework actually can identify nodal points which can help to predict, let's say, combination of stressors which deviate from addition of the risk, so to better characterize synergies. This is the Radon AOP working group. Actually, we tried during this 5 years of Radon to make all those people interact. I also want to stress that many of the data on radon that are present in Wiki AOP were made by Vinita Chouan from Health Canada. She gathered the information, yes, to produce this AOP. I indicate here all the different publications and achievements that were made, and I thank you very much for your attention.